All right. Give it a couple more minutes. People are filing in.
Mike, I'm not sure if you know this, but these weekly colloquiums, they are actually a course called what is it? 495, 595A, I believe. So the students who are enrolled in this course, they're required to take these.
They're all going to write a report.
And they have to write a report.
So if you want to have feedback, Mike, I can ask them for permission.
Yeah, maybe I could give a quiz at the end.
Yeah, that would be great. You've never had a speaker give a quiz.
I'll let you know when we ring the bell so I can.
Sure.
How are you running the Colloquium in Oregon? Are you running live colloquia at Oregon, Mike?
Yes, it's a hybrid. Sometimes there's an audience. Well, if the speaker is physically present, there's an audience, but then usually if the speaker is not physically present, we just do it virtually.
Yeah. All right. Okay. We're ready to ring the bell.
Just let me know when we should get started.
All right. I'm ringing the bell, Sycat.
Okay, sounds
Go
good.
for it.
All right. Thank you very much. It's my pleasure to introduce Professor Mike Raymer, who's our colloquium speaker today. It's a real honor to introduce Mike, who's one of the pioneering founders of many things in quantum optics. And Mike, I don't know if you can hear me, Del. I'm hearing some feedback from the room. Can you hear me okay?
We can hear you. I would say
Okay.
that anybody on Zoom who has a microphone, please turn it off. Yeah.
Yep. And whoever is the host on this meeting, they can mute everybody if you want to. But looks like it's gone now. So I'm sorry for the interruption. So Mike is a professor of physics and a Knight Professor of Liberal Arts and Sciences at the University of Oregon. Mike is really well known for his work in quantum optics, atomic molecular physics, and broadly quantum information science. Some of the things that he has been recently been interested in and working on are manipulation of single photon states for use in quantum communications and remote sensing systems, 2-photon entangled states for probing the structure and dynamics of molecular systems. Mike has done some really interesting work on nonlinear optical transformations of multi-spatio-temporal modes of light for applications both in classical and quantum optics. Many of you may know Mike's leadership in the last few years, working with Chris Monroe. He led a really tremendous national effort to lobby the US government to support research in quantum information science and technology that led to the passage of the NQI Act in 2018, which is what resulted in all of this funding across the country in various aspects of quantum information science engineering. So we're really grateful for Mike to have led that effort. Mike is also a PI on our Center for Quantum Networks, and as part of which he has been working on a variety of things, including quantum network tomography. And you'd be interested to know that Mike was the one who actually coined the phrase quantum tomography in his early paper on this subject that has become its own subfield. Mike did his undergraduate degrees in physics and chemistry from UC Santa Cruz, and he did his PhD from UC Boulder. And he was at the faculty with University of Rochester briefly before he moved to University of Oregon in 1988, and he has been there since then. He's the founding director of the University of Oregon Center for Optical, Molecular, and Quantum Science with it's my real pleasure to have Mike speak on a topic that's been of interest to us here lately a lot. He has been working on using entanglement for enhancing the performance of long baseline telescopes. So Mike, take it away whenever you are ready, and share your screen, please.
Okay. Okay. Is that showing up correctly?
Yes, it is. Thank you.
Okay, thank you very much, Saikat, and welcome everybody. I could see from the gallery many friends and colleagues, and I'm very happy to be talking with all of you. As Saikat said, this talk is about quantum enhanced telescopy, namely telescopes, but I'm not a real astronomer. In fact, I'm not even a fake astronomer. I'm a quantum optician. So while Tom Koch showed me the very large mirrors that are being fabricated and polished on your campus, our mirrors, our telescopes are much smaller. They're basically the size of a single mode optical fiber, the smallest possible telescope. You'll see how that all works out. It's a simulation proof of principle experiment. So the idea is to use the single photon states as a non-local oscillator, and I'll explain why that is a good thing. Our collaborators at the University of Oregon are Matthew Brown, Valerian Theo, Marcus Algeyer, and Brian Smith. And we're part of a NSF-funded group grant led by Paul Kwiat at Illinois. And our astronomer member is John Monnier from the University of Michigan. And he's the one who asks us all the hard questions and keeps us honest about what we're really trying to do here. And additional members are Eric Chambar and Gina Lorenz and Andrew Jordan. So onward. Okay. Well, the goal here in a nutshell is to develop a very long baseline or a VLBI scheme, which of course has been known for almost, well, over 100 years, actually, close to 100 years. I hear some talking in the background. But we want to try to use quantum information processing to enhance the performance. So the state of the art is roughly a 300-meter baseline, for example, the Chara Array. And this can yield a milli-arcsecond resolution for relatively bright astronomical objects. Do you see my cursor moving around here, Saikat?
Yes, I do.
Okay, so down here is a couple of papers by our colleague, John Monnier, who's worked on many different implementations of VLBI. Pioneering work is what he did, actually, working in part with Charles Towns for his PhD. But these kind of techniques are limited by shot noise or losses or, of course, turbulence in the atmosphere, which I will not address, by the way, and also just the requirement to observe bright objects. So the long-term goal here would be to achieve, microsecond arcsecond resolution, micro arcsecond, which would be a few orders of magnitude improvement over what can be done now. Now, to do that, you just need to have a longer baseline. Well, you might know that the Event Horizon Array observed a black hole in the radio frequency regime using a very long baseline, which was the size of the Earth. We cannot implement those same techniques in optical, however. So we need other tricks. Now, the impediment is basically, typically you have to combine the beams from different telescopes over some long path. And either that, or you have to use a local oscillator, which introduces shot noise in the detection. So the baseline, which we call little b, is limited to roughly a kilometer. In theory, you could go to tens of kilometers if you had very long vacuum pipes like the LIGO instrument, but that gets to be problematic. So the proposed solution, which has been around for about 10 years now, is to, instead of using a laser as a local oscillator, as shown down here, you would replace the laser with single photon source and beam split it on a few beam splitters and send it off to all these different telescopes and then compare the measurements at these different telescopes. So the measurements are local because at each telescope, they just have detectors. They record clicks or no clicks. But the oscillator, which is normally called a local oscillator, is actually we call a non-local oscillator because it provides a kind of a quantum non-locality or entanglement resource between the telescopes. So our initial experiment, which I'll explain at the end, is just using 2 telescopes, which are, as I said, optical fibers, and 1 non-local oscillator photon. And basically it works. Okay, so that's the executive summary. So you can go to sleep now if you like. But the history of this subject is of course, a very well-known and long one. And that is that Michelson, 100 years ago, actually to this year, this is the 100th anniversary of this experiment. He essentially had 2 telescopes and he combined the optical fields from a single star or a binary star and looked at spatial interference patterns. And then as he changed the phase and the separation of these telescopes, you could see how this interference pattern changes. I'll explain why that gives you imaging. It's basically a synthetic aperture with 2 apertures. Okay. Or you can also do it this way with a 50-50 beam splitter where you combine the paths on a beam splitter and look at just 2 detectors instead of spatially resolving and imaging or scanning this interference pattern. Well, sometime after that, 30 or 40 years after that, Hamburg, Brown, and Twist did this famous experiment where they had 2 telescopes and 2 photomultiplier tubes, and they collected light from 2 mirrors. And they mixed the intensities, namely the electronic currents, which reflect the intensity of the incoming light beams, on a linear mixer, which is a multiplier, basically, and a rectifier. And by looking at the fluctuation statistics between these interference between these 2 telescopes, as a function of the distance between the 2 telescopes, you could again reconstruct some spatial information about the star that was emitting the light. Now, then later, Charles Townes introduced heterodyne detection, where he has a classical laser, which is a local oscillator, or sometimes you can use 2 separate lasers that are phase locked, but they're classically connected and synchronized. So you send this laser out into 2 different directions and you do homodyne detection. We call this balanced homodyne detection in the quantum optics world. And then you look at these currents, and as a function of the separation of the 2 telescopes, again, you can reconstruct the star. So Gottesman just replaced the laser local oscillator with what we call a non-local oscillator, which is some kind of a quantum resource, because a classical coherent state laser does not produce entanglement at the 2 telescopes. Whereas if you use a quantum field and distribute it, you can produce entanglement. Okay, so this is just an old review paper from JPL explaining the concept, which many of you are probably familiar with. Here's this distant source of thermal light. It has some spatial distribution. Maybe it's 2-point sources. And these incident phase fronts, you can think of this light as coming through a gigantic beam splitter because it essentially goes in 2 different paths. It really goes in 1 million paths, but you only detect 2 of these paths. So you can think of that as a very large beam splitter, splitting the light from this distant source into these 2 telescope apertures. And then you use optical delay lines, which have to be adjusted to lengths D1 and D2. So the photons, any given single photon, this is an important point, we're not interfering 2 photons here. We're just interfering 1 photon with itself. But that single photon can take 2 different paths and then produce, Michelson type interference fringes at the beam combiner. And then you can use a photomultiplier tube to just count clicks as you vary a phase and also the baseline B. Okay, the probability to get a signal in this case is just given by this, interference pattern 1 plus cosine the baseline projected onto the distant source direction, S minus the 2 delays. Okay, so this kind of technique has been around, like I said, for a long time. I just want to point out that in this paper from JPL, they referred to this direct Michelson technique as homodyne because you're interfering light with itself. But in quantum optics, homodyne means we interfere the light with a local oscillator with the same frequency, and heterodyne means you interfere the signal with a laser with a different frequency. So when I say homodyne, I mean, that's what I mean, is the quantum optics sense in the way that Charles Towns was using that. Okay, so the Avancidar-Zernike theorem is well known to those who know it well. And what it says is that if I have a source of thermal light that's distributed over some region with a distribution called I of X for the source, and then that thermal light comes down to these two telescopes, et cetera, there's a speckle pattern, of course, which is produced. And the spatial coherence function as a function of the transverse position, namely Y, which we could label as the position YL for the left telescope receiver and R for the right telescope. That 2-point field correlation function is given by the Fourier transform of the intensity distribution at the incoherent thermal source. And then this is the, just the sort of Fraunhofer propagation from the diffraction theory. So if you can measure this 2-point correlation function and then inverse transform it, you can deduce the spatial distribution at the star. So the way that's done is to introduce notation. The square of this is 1 plus the visibility, the magnitude of the visibility V. B is the baseline, which we're going to vary. And then there's a cosine. The phi is the phase, which depends on the baseline, but there's also delta, which is this introduced phase that the experimenter introduces and scans from 0 to 2 pi. So you vary this delta and you observe this cosine changing, and from that you can deduce the magnitude of V visibility and also, if you're lucky, the phase. So once you have that, you can normalize that if you like, and then, as I said, you inverse Fourier transform this, and that gives you the intensity distribution at the star. Well, this method works, and here's a picture from a paper in 1997. Just showing how it might be set up. In this particular case, they use optical fibers, which is also how we do it. You have the light coming into two telescopes, which are just big lenses. You couple those into single mode fibers. You send them to a fiber beam splitter called X, and then you look at the interferometric outputs here. Now, in this talk, we're going to assume that the atmospheric correction is done perfectly by our friends who know how to do adaptive optics. We're also going to assume that the path differences or paths between these the phases between these two paths are stabilized. Okay, so here's the Chara Array, and here's our colleague John Monnier, who co-authored this nice review paper. And you see that the baseline between these two telescope locations is about 300 meters, and there's 6 of them, and here's the central spot where they combine all these beams through vacuum tubes under the ground. And here's an example. Well, here's John looking through a laboratory telescope on the table. And this is one of the early images that they were able to reconstruct. I think MAS means micro arc seconds. So they're able to reconstruct this image of a main sequence star other than the sun in 2007. All right. Now, again, the Hamburg-Brown twist, in more detail is again, you look at the intensities between these two telescopes, you multiply them together, and you look at how much fluctuation there is as a function of the separation. And as you vary the separation, the baseline, you get this loss of visibility. And from that, you can deduce, again, information about the star. But in this case, it requires high intensity because you need to have 1 photon in each telescope at least, so you can get intensity correlation measurements. So that's limited to very bright sources. Then there's the Heterodyne receiver, which I mentioned earlier, the Towns scheme, which I mentioned earlier as well. They operated this at 11 microns in the infrared. And again, they have a local oscillator. So you have this laser, or in this case, 2 lasers, which are phase locked to each other. But as we know, a laser introduces shot noise, which means that in any finite observing time, detection time, like say 10 nanoseconds, the laser is going to deposit a random number of laser photons onto your detector, and the distribution is given by a Poisson distribution. So when you have very low numbers of photons, which is what you want, the shot noise can be overwhelming. So this limits then the usefulness of the technique, and it's typically not used these days. Radio heterodyne interferometer, fortunately, is less affected by shot noise because of the wavelength is so different. They don't have to worry about shot noise in that case. The photons are sort of not really present. It's really more like a wave phenomenon. Wave particle duality favors the wave interpretation, and the shot noise doesn't really come into play. So this is why they could use radio receivers to reconstruct the black hole image. Okay, so moving along, how are we going to combine all these ideas into a new idea? Well, we ruled out Henbury-Brown twist because it requires 2 photons. These 2 methods allow detecting 1 photon from the star by either interfering it with itself or interfering it with a heterodyne or homodyne laser. The challenges are the shot noise, low loss, low signal transmission through the paths that you would use to combine them, and sometimes the requirement of bright objects. So Gottesman came up with this nice scheme back in 2012 with colleagues Genuine and Croak. And they put out this nice paper, and a few other papers came out soon thereafter analyzing this problem in some detail. And here are some other proposals that I won't talk about in much detail. So there are a number of different ways you could do this. Now, there's a very nice paper by Man K. Sang, who analyzed the Gottesman scheme, and he proved the following: comparing this direct method with the Gottesman non-local oscillator method, he proved that using Fisher information, these 2 schemes are equivalent to within a factor of 2, and they outperform all classical local measurement schemes. So they outperform intensity interferometry, they outperform homodyne and heterodyne and any other scheme you could imagine that doesn't involve either directly combining the fields as here, which is a non-local measurement because you're taking light from the 2 telescopes and you're processing them and measuring them, or uses a non-local oscillator, which effectively makes a quantum non-local resource that mimics what would happen if you brought the 2 signals together. But in this case, you distribute the quantum resource out and you interfere it with the 2 local telescope outputs. Now, the factor 2 loss of information is because in this case, as I'll say in detail later, you have to wait until you see 1 click on this telescope and 1 click on one of these detectors at this telescope. If 2 detectors click on the same telescope, you get no information because you're not probing interference. So that's why you lose a factor of 2 as far as information per photon detected. Okay, but we can outperform, we think, this loss of factor 2. And in the limit of very large baseline separations, we think we can, in principle, outperform the direct method. Okay, so here's the scheme that Gottesman et al. Proposed. This is from their paper. You have these objects. 1 photon comes down from the star, and there's a baseline B between the 2 lenses of the telescopes, and that's going to be varied. And here's these 2 beam splitters and detectors. And now we have a single photon source that may be a quantum dot. Then you push a button and 1 photon comes out, or it may be some other source. And it's in a well-defined temporal, spectral, spatial wave packet, as I've shown. Now that photon hits a 50-50 beam splitter here, and it produces an entangled state. It produces an entangled state between these 2 paths. It's a path entangled state. Or you could say, if you think of these paths as optical modes, you could say this is mode entanglement. It's not entanglement of a photon because there's only 1 photon. You could say it's a superposition state of a single photon, but that corresponds to an entanglement of the paths or of the modes. And here's the way you write it: 0, 1 plus 1, 0 with a phase shift delta, which is introduced here by the experimentalist. And you vary that. And you look at clicks on these 4 detectors as a function of that phase shift delta. And from this, you're supposed to learn about the objects. Okay, now the problem is we want to extend the baseline B over much farther than 1 or 10 or 100 kilometers. Well, in principle, you just have a long vacuum pipe, which is 10 kilometers long, and you send your photon through there, but that's not very affordable. Ultimately, if the pipe is long enough, it needs to wrap around the Earth. So you might use optical fibers to send that photon, but then the problem is you're going to lose exponentially the probability that the fiber makes it all the way to the second telescope. It's going to be lost. So how do we overcome that? Well, here's a picture that Sykot is very familiar with because it's copied from one of his papers a couple of years ago. We have a quantum internet, and we know that Sykot is in the process of building such an internet. So as soon as we have that, in 1, 2, 3, 5, or 15 years, we'll be able to take this half of the entangled path state and essentially teleport it through this quantum internet over to the other telescope. And it's known that if a quantum internet works perfectly with quantum memories and entanglement purification protocols and so on, that it can greatly outperform the exponential loss with distance that would be obtained by using just a single fiber path. So that's the idea. You have this one photon here, you beam split it, you produce entangled paths, and then you teleport this half of the entanglement over to the other telescope. Well, this is an idea that was proposed by the Lucan group, as I'll get to in a minute. So unfortunately, here's the practical problem. And if there are any astronomers watching this talk, you probably thought about this already. And it's really the showstopper that has to be overcome. The problem is that light from a star, it's thermal. And we know that the occupation per mode of a black body thermal source at reasonable temperatures, even the surface of a star, is much less than 1. I think it's like 0.01. So it means that any space-time mode indicated by these little circles here would be populated only with a probability of 1% or less. So here I've shown time windows of 100 picoseconds and frequency bins of 30 gigahertz, which produces a coherent area in phase space. This is one way to label modes in space-time phase space. So the problem is we have our nice single photon that came out of our quantum dot when we pushed our button. But most of the time that photon is wasted because it comes at some other time when there's no photon from the star. Now, I admit that I'm taking an overly classical viewpoint of the quantum state of starlight, but I think the bookkeeping works out to be the same way. In other words, you can't really say that a star emits a photon at a certain time. It's all quantum, but still on average, the rate of photons arriving per frequency, per time interval is very small. So ultimately, which I'll get back to at the end, you have to do very high levels of multiplexing. So you would do something like this. You have your laser, you produce some kind of single photons, you beam split it, and you might have to frequency resolve the photon. Well, I'll get to this detail later, but basically you want to send a bunch of broadband photons or many photons of different colors to your different telescopes, and then have many different, not just 4 detectors, but 1,000 detectors, 500 pairs of detectors at each telescope, and then correlate all that information so you can access information across the a larger optical range than you can with just looking at a single interference. Now, going back to the Michelson case, why does that technique not suffer? That's because it's basically white light interference. And we know that if the path length, relative path length in an interferometer is close to 0, that white light does interfere with itself. But when you use a local oscillator, that's not the case. The local oscillator has to be in the same mode as the light you're trying to interfere with. So I'll get back to this later. Now, there's this paper by the Lucan group at Harvard that came up with a hypothetical solution to this problem. So here we have the cloud, which is the quantum internet. And the quantum internet somehow distributes entangled photon pairs to these 2 memories, which are located many kilometers apart. And they're stored there coherently, and their phases are known. This is very difficult to achieve in practice, but in principle, the phases could be known by using advanced atomic clocks or some other method. And basically, you need to have a way of monitoring when the photons come in, sort of collapse the star wave function into a certain time window, and then release one of these stored photons from a memory, which are on demand. In other words, you have pre-populated these memories with photons. And they're all the time frequency slots are filled with photons just waiting for the star photon to come in, and then you process it. Well, this is nice in theory, but we certainly don't have any of this technology and probably won't have it for 10 years. So what can we do here? For now, we're going to emit this state teleportation and the memories, and we're just going to do a proof of principle experiment and test the basic theory of this. So the way we make a single photon is not with a quantum dot, but rather it's a pulse laser, puts out a blue pulse of light. It goes into a crystal called a spontaneous parametric down conversion crystal, which splits the blue photon into a pair of red photons. One of the red photons goes into this detector, and if it clicks, we say there's a herald, which announces the presence of this other photon. And now we have a single photon at a known time in a known temporal spectral spatial wave packet. So we send that photon to our beam splitter, and then we send it to our two telescopes. We introduce our phase shift, and away we go. We make measurements of fringes, and we vary the baseline, and away we go. This is essentially the experiment that we have done recently. But there are many problems here to deal with. One is the starlight is not a short pulse. Starlight is stationary or steady state. So is producing these noisy looking steady state signal, which is beam split and sent to the two telescopes. So first you have to put it through a narrow pass spectral filter. And then you have to use very fast time detectors, time response detectors, such that the time frequency bandwidth product is about equal to 1. So again, you're throwing away most of your starlight in order to make this work. Okay, we have not done this experiment yet, but we will do this one in the near future. Okay, this just illustrates that point a little bit more. You have a steady state, a thermal light coming in with a very broad bandwidth. You put it through a spectral filter with a bandwidth B, and then through a time gate, which simulates what a fast detector can do with duration T. And if B times T is equal to 1, then you create the optimally filtered wave packet, which then it's not perfect because you cannot convert noise into coherent field with high efficiency, but you can do that with certain efficiency, maybe 50% efficiency, but there's always some residual noise here. And then you can interfere that now with the well-designed single photon local oscillator, which is a pure coherent wave packet. And you get not so bad interference. And this does work in theory. Now on to the actual experiment. Let me check my time here. Okay, I think we'll make it. We started at 2:45. So the proof of principle experiment that Matt Brown is doing for his PhD thesis with the assistance of two postdocs, Valerian and Marcus, and supervised by Professor Brian Smith, is the following. He's going to somehow make a short pulse of thermal light with the known intensity distribution I of x, say a small Gaussian. That light is going to diffuse out through free space and hit our two telescopes, which, as I said, are simply single mode optical fibers. They collect a little bit of light in each one, but the light is so weak that there's only one photon that arrives in this wavefront at any given time within a coherence time. And then we have our SPDC source pumped by blue pulse producing the heralded single photon, which is split into the entangled state, which is controlled by the phase shifter delta. And the trick that we're using right now, which is kind of cheating, is we're using a short pulse to produce our thermal light using a diffuser, by the way. And it's temporally matched to our laser pulse that produces our single photon local oscillator. So we've automatically beat the temporal spectral mode matching problem by essentially cheating by making a simulated star that has the proper properties so we can interfere it with our single photon. But as I showed on the previous slide, we could also do this by filtering, which will be our next project. Okay, so the probability so here's how we do it. You never know when a coincidence count is going to arrive. You're shooting this laser at 80 megahertz, and then maybe every once in a while, 10,000 or 100,000 times per second, you get a coincidence count, one on the left, one of these two clicks at the same time, one on the right clicks. Now, here's essentially the key point. If there's only one photon from the star and one photon from the local oscillator, and you get 2 clicks, well, that's everything. So in other words, the local oscillator is a Fock state or a number eigenstate. So there's no shot noise. So this is why it's like a local oscillator, but without shot noise. That's really why you win. Now, of course, the star can have 2 photons and the laser can produce 2 photons, and those are impediments, but we can estimate the negative effect of those impediments. So we're modulating this phase change here with the PZT, moving the PZT at a 600 hertz repetition rate. And we don't know when the event's going to happen. So you can say it this way: when you get a click, what's the probability that the phase value was a certain value delta? And that probability is given here. P of delta is 1 plus the visibility cosine delta minus phi. So yeah, that's right. And you know what delta is, well, because you're tracking delta. And so this gives you information now about phi, as I'll show. So the complex visibility, again, is a Fourier transform of the intensities distribution. As I said, here's a Fourier transform written out in a discrete form. If the intensity distribution of the source is I sub j, where I've discretized it, then this is a discrete Fourier transform. But you can, of course, convert that into a continuous integral transform. And then there's this temporal mode overlap. The A of L is the single photon local oscillator. No, that's not true. That's the starlight. L means light from the star. It's red. And A sub LO is the single photon local oscillator. And they're both in wave packets. Ideally, they'd be in pure state, time frequency, transform limited wave packets. And you have to overlap those and do a time integral and square that. And that gives you the extent to which they can interfere. And there's other factors here which may degrade the visibility if there's multiple photons from the star or accidentally multiple photons in your local oscillator, and you don't properly implement the heralding protocol so you can know when there's only one photon in the local oscillator. So one thing we do is we turn the heralding on and off, and we see if there's a difference in the results. So to walk you through the apparatus in more detail, here's our mode lock titanium sapphire laser, 830 nanometer wavelength, 300 femtosecond pulse comes out at a rate of 80 megahertz. There's a beam splitter, some 50-50 splitter. Part of it goes up through this path here and produces a thermal-like light or quasi-thermal light by the old famous classical optics trick of a rotating diffuser. So it's a rough piece of glass or a rough piece of plastic, and we rotate it on a motor. And if we split this beam into 2 beams, we can make a binary star simulation. And if there's only 1 beam, we have a single star. And now it's going to diffract out and it's going to hit our 2 telescopes. Well, it's hard to put 2 fibers really close to each other. So we use optics. You know, it's all done with mirrors, and it's a trick. So some of the light transmits through the beam splitter and hits this telescope fiber, and 50% of it reflects off of this beam splitter and hits this other fiber. This is a non-polarizing beam splitter. So it's just as if you could put these 2 fibers on top of each other and then scan the distance between them. Okay, now let's prepare our local oscillator down here. We do that with a BBO crystal, which first produces red light. Turns red light to blue light, and then goes into the PDC crystal, which produces a pair of red photons. One of those hits a herald detector, which goes off to our electronics. And the other one goes into a fiber and then interferes on a fiber beam splitter with the 2 paths, as I showed in the earlier schematics. It's split into 2 paths. Each path can interfere 50-50 with one of these fiber outputs. Now you might wonder, well, there's only 1 photon coming from the star, so how can you get interference on both? But that's quantum mechanics, right? In fact, it also works classically because light is really a wave. The wave splits, either the classical wave splits or the quantum wave splits, and interference of waves occurs everywhere where the amplitudes overlap. Of course, when you detect it, the whole thing collapses to 1 photon. but the interference still is present. So we use a PZT to move a mirror to change this phase in this triangular form here at a rate of 600 Hertz. We scan the phase. And then we look at coincidences between these 4 detectors. Okay, so I should skip through the math here a little bit, but you know, it's interesting actually how you process the data. What you do is each time you get a coincidence count, you look up on your phase table, because you're tracking this phase of your PZT, and you say you get an event at time t1. Well, you just look up here, you say, the phase at that time of the event was delta equals delta 1. And then you calculate the phasor, e to the minus I delta sub 1. And now you get a complex number. Then you do it again. You wait till the next coincidence occurs at T2, and now you look it up. Delta was equal to delta 2. So now you add that to your average. And you do this, you know, hundreds of thousands of times. And you end up with the ensemble average of the phasor, which is labeling each of the coincidence events. Well, that's the same thing. Well, this is like the ensemble average of this phasor over n events. And you can prove from this little probability formula here that that's equal to the complex visibility. That's, again, well known to those people who know it well. Now, there's a problem here. If you don't control your interferometer drift well enough, you can't actually extract the complex visibility, V times e to the minus I phi, but you can still extract the magnitude of visibility. And that's what we've done so far. And that is sufficient to analyze certain simple sources, like a source with a symmetric spatial distribution. Okay, so now we're getting near the end, and we're showing the results that Matt Brown accumulated over, I don't know, 20 minutes of data collection or something. So for each telescope baseline fixed, which means he moves one of the optical fibers a known number of millimeters away from the location of the other fiber, then he sits there, he does his phase modulation, he does his phasor average, and he extracts from that the magnitude of the visibility. And as advertised, at 0 baseline separation, you get maximum visibility. And then as you move the 2 telescopes apart, the visibility decreases. Now, physically, again, the reason for this is simply, if you like, there's a speckle pattern. And light within a given speckle is phase correlated, but light between 2 different speckles is not phase correlated. And so if you try to interfere light by capturing light with 2 fibers from 2 different speckles, they simply don't interfere, at least not on average. And so the interference visibility drops down. That's what's the basis of all these techniques, really. But here we've shown it also works for single-photon non-local oscillators. Okay. The error estimates here are just from repeating the whole process 10 times and computing the standard deviation. Now, this is from the heralded single-photon non-local oscillator with 1,600 events per point. Okay, by events, we mean successful coincidence events. So it's not photons coming through the telescope, you know, per second, or the total number of telescope photons coming through, because most of those are not detected. We have to wait until we get a coincidence event, which means we have seen interference between the starlight and our local oscillator photon. Okay, but that is a reasonable way to parameterize the result. Now, here's what happens if we turn off the heralding. So when you turn off the heralding, you simply don't look at that heralding detector. And now what happens is your local oscillator pulse may contain 1, 2, or 3 photons. And it might even contain 0 photons, in which case you would see interference if there were 2 photons from the star. So all those noise events or impediments changes the result. The main point here is not that the value is lower, because the signal to noise is about the same, but the main point is that to obtain this blue data, without heralding, we had to take 10,000 events per point to get a reasonable result. Whereas with the single photon heralded, we only need 1,600 events per point. So this is at least a qualitative indication that we're getting more information per heralding, per coincidence event when you herald and when you don't herald. So there's a lot that needs to still be
That
done.
little inset, did you put that there for Mike did?
Which one?
Fourier transform reconstructs Gaussian source profile.
Well, yeah, I can comment on that. Thank you. There's inset up there. So when Matt takes this data here, which is baseline, and then function baseline, does a Fourier transform, then he reconstructs the actual source back at the diffusing rotating screen, and he gets the correct result, which is a single Gaussian peak with a diameter of about 0.2 millimeters. So again, qualitatively, or I should say semi-quantitatively, showing that the method actually does what you want to do. So next thing we have to do is to do like a binary source and then more complicated sources. Thank you for that question. Now, so therethere's two more slides showing you what our future experiments will be. One is to replace our pulsed source, which I said was cheating, with a CW or steady state quasi-thermal source. So we'll simply use an LED and put a spectral filter with a bandwidth delta nu and put that onto our rotating diffuser, put that here. So now it's continuous, and but it has been filtered down. And so now we have to have a time resolution of our detectors, which by the way are superconducting nanowire single photon detectors. They have to have a resolution delta T, which is of order the inverse of the filter. And so this restricts how narrow the filter, or how broad the filter can be. So we can do this experiment. We should do that in the near future. The other thing we'd like to do is not be restricted to just a single spectral filter. So what you'd really like to do is replace the spectral filter with a diffraction grating and spread, probably back here, not at the star. It's kind of hard to put the filter at the star, but you could put the filter down here before the telescopes and replace that filter with a diffraction grating and demultiplex all the spectral channels, and then have many fibers that go to many detectors, each of which has a time resolution delta T, which allows you to see visibility. So the way that would look, again, I showed that earlier, would be something like this. Starting on the right-hand side, you have a laser pulse. It sends out a stream of photon pairs. The photon pairs are broadband. They can cover a very broad spectrum, like say 80 nanometers of wavelength range, which is more than enough. And then you put the heralding photon into a frequency demultiplexer, which again could be a diffraction grating, and then an array of many nanowire detectors. So we need to collaborate with detector array fabricators, such as the people at NIST or at JPL or MIT, to produce these. And then you take this single broadband photon and you beam split it and you send it off to all the telescopes. And at each telescope, you frequency demultiplex the starlight as well as the single photon local oscillator light. And then you have an array of 1,000 detectors here, and you have to collect many thousands of counts all in parallel and process that. So in principle, this should start to become competitive with the classical techniques, which can automatically utilize the broad bandwidth. Okay, so we don't need quantum memories here to do this, but at the same time, we cannot use this picture on screen to extend over 1,000 kilometers because we'll be losing our local oscillator photons along the way. But at least we can address the time bandwidth challenge with this setup. Okay, so in conclusion, Matt and team have carried out a proof of principle experiment showing the Gottesman et al. Protocol with 2 telescopes and single photon local oscillator, non-local oscillator, and local measurements. And it's consistent with the idea that that's equivalent to non-local measurements, which means combining light from different telescopes. In this case, we don't have to combine the light from 2 telescopes. And we can outperform the classical local oscillator, as I mentioned. We demonstrated source reconstruction for a simple source. We increased our visibility by heralding. So when you don't herald, as I showed, you get less visibility per coincidence event. Now, not heralding is a way to simulate a classical local oscillator because there's no entanglement in that case. And I can answer more detailed questions about that if you don't believe that later. Scaling to higher rate of heralded non-local oscillator photons. So if we can make a faster single photon source, we can do better in principle. But to win, we really need to increase the single photon rate to be very fast and fast detectors with more efficiency, and demonstrate this with continuous thermal sources and reconstruct complex structures of CW thermal sources. And we need a massive demultiplexing of local oscillator photons and possibly teleportation to quantum memories, which could be in the future. So my final comment, well, first of all, I'd like to thank all the collaborators that I mentioned on the first slide, but in particular Matt Brown for carrying out these experiments. And then finally, just want to mention that our team has put in a white paper into the NASA decadal survey proposing that NASA support the development of such a telescope over the next decade. So with that, I will end, and thank you very much.
Mike. Dal, would you like to start with the questions in the room? Chuntao has his hands raised. Why don't you go ahead and get started, Chuntao?
Yeah, thanks. Thanks, Mike, for the nice talk. I really learned a lot. So I have a question about the single photon assumption or fact of the astronomical objects. So it's intuitive that if you have more photons coming in, then you would benefit from that because you have more information, but looks like the visibility will decay in your case. So what is that reason? And then another question is so that formula you have in the beginning, EY is the Fourier transform of the pattern of the source. Does that also work for multiphotons, or is it just for single photons?
Well, that works for a field. The field can be classical or it can be a quantum field, the operator. And so the formula still works, but of course, when you go to the measurement theory, you have to modify that. So the point part of the point of this work is to look at very dim sources and sources that are farther away, so they're naturally dim. So we don't really address so much the question of what happens if the source were much brighter and you had multiple photons coming in. And I agree, there might be different protocol that would be more beneficial in that case. But we assume we're in the limit where certainly it's always true that the number of photons per frequency time mode is always less than 1, because stars simply are not hot enough to exceed that value. And so that's always, by mode, stars are always dim. Now, if you have multiple photons coming in a time window in different modes, well, you might have to demultiplex that somehow. But again, that's not the goal of our work.
Okay, I see. Thanks.
More questions for Mike?
Hi, Mike. This is Jason. Thanks very much for the great talk, and it's a fascinating experiment. So I probably have a pretty rudimentary question about what are you trying to measure in this visibility measurement? So what kind of information are you probing? I'm sure you probably touched upon this in the beginning part of your talk, but I just wanted to know a bit more about that.
Right. So the goal of these kind of experiments primarily is to image the source. So I use the example of the black hole, imaging that black hole. And the other example I showed was imaging the surface of a star and showing the temperature distribution or the brightness distribution across the star. If it's a binary star, then you can measure the separation between those. So it's really imaging. In principle, you can do spectroscopy if you can spectrally resolve the image. But I think typically people just fix a bandwidth within some nominal wavelength range and just look at a grayscale image of the brightness of the distribution.
I see. So then in your experiment, I think you extrapolated a distribution in your data that a distance. So what does that correspond to in your actual apparatus?
Right, right. So in our case, we've only done a single Gaussian distributed source so far. It's the most boring case you can imagine. So the only parameter you can measure is the width of that Gaussian. In our case, it corresponds to the width of the laser beam that hits our diffuser. It's about 0.2 millimeters in size. So we know the distance, which is 1 meter, to our diffuser, to our telescope. And so we use the Avancidar Zernike theorem and our interference data, which is visibility versus the separation between the two telescopes. And we can back calculate by Fourier transform the actual distribution of our source, which we show it's Gaussian and it has the correct width.
Mm-hmm.
So like I said, that's kind of boring. If we do a binary source with two Gaussians, that would be much more interesting.
Right, but I think it's an important step, what you have done.
It is very important.
Yeah, thank you.
Yeah.
I believe there was a question in the room. Somebody just got the microphone. Can you speak a little, hold it closer to your...
Testing, is this thing working?
Yes, it's working.
Okay, thank you. Thank you again for the presentation. Just a follow-up. At the beginning of the presentation, you characterize your system using Fisher information. What is the Kramer-Rao lower bound you expect for this kind of system, this kind of imaging system?
I don't know the answer to that question.
The variance on your estimator.
I don't know the answer to that question either.
Okay. I guess then just to follow up, given you're adding a diffraction grating to demultiplex the signal, do you not expect that to affect, the recovery of the visibility of your source?
Well, the diffraction grating in our future experiment will simply spread out the starlight into different spectral channels, and then we'll apply the same method that I just showed separately to each channel. And so we'll just then be able to add all that information together. And in fact, you could even do spectroscopy that way, but just to get a grayscale image, you would just add all those together. So you just don't have to wait as long to get the data.
Let's go with more questions in the audience, in the room.
Another question for you, sir. Thank you again for the presentation. So 2 questions, actually. First one has to do with the heralding, and maybe this is a little bit simple, but after your photon has gone ahead and been detected by your herald detector, what kind of coherence length do you have on the other arm of that before that information is kind of lost?
Mm-hmm. Right. So in free space, we know that photons can travel infinitely far without decohering. And that's why they are the preferred, object for communications. So in our case, it would be the vibrations of the optical fibers, which are not fully nailed down, or temperature drifts of the fibers, or when you come out into free space before you go into another fiber and fiber coupler, again, you can have vibrations or drift of certain optical elements. So it would just simply be not so much a decoherence. It's not that the photon becomes incoherent. It's that you're not controlling the mechanical path lengths well enough. But in principle, you could send classical laser beams in parallel through the same network and stabilize this phase or measure the phase drift in real time.
Gotcha. Thank you. And then the second question, at the end of your presentation on your final slide for the future, you mentioned wanting a better white light source that is broader. Have you guys considered using supercontinuum generation for that thermal light source? And if so, what's the central wavelength you'd actually need for that generation?
Right, so our current experiment is at 830 nanometers. And so you can certainly generate supercontinuum by having a very strong laser pulse go into an optical fiber or a piece of sapphire or something. The supercontinuum is complicated. It's not really a thermal-like source. In fact, in some regimes, it has phase coherence across the entire spectrum, although the phase structure is extremely complicated because there's soliton breakup and so on. So we thought about that, but decided not to try supercontinuum because we would end up probably studying more the supercontinuum physics than anything else.
Awesome, thank you.
Mike, I had a question that's related to that, and I had discussed this seeming paradox with Chunta one time, and I still haven't fully resolved in my head. So I wanted to ask this to you. So when you take a thermal light source and split that on a beam splitter, the quantum description of the light you get on the output of that beam splitter is a classically correlated zero mean Gaussian state. It's not an entangled state. Whereas if you split a single photon Fock state on a beam splitter, you get an entangled state on the two outputs of the beam splitter. The true quantum mechanical description of a single polarized, spatiotemporal polarization mode of that starlight that you described is actually a zero mean phase insensitive multi-mode Gaussian state. It's the kind of state you would get by taking a weak thermal source and splitting it on a huge beam splitter network. So it's not an entangled state. On the other hand, if you look at the quantum state that Man-K Sang wrote, or Daniel Gottesman wrote, or even Michel Lukin wrote, their state is an entangled state because they assume it's a single photon split in this gigantic beam splitter array. So my question is it that, let's forget about the losses on your fibers that you're using to send the entanglement. Let's say it's all local in one place. Can you mimic the action of this non-local measurement by, instead of splitting that single photon on that beam splitter before you put that delta phase, is it possible for you to take a thermal source and split it on a two mode and use that instead to do this, the same measurement? Or is there a fundamental benefit from having that 1, 0 plus 0, 1 kind of a state to get that measurement result?
Yeah, thank you for that question, because it allows me to restate what I tried to explain when I talked about the data, because I showed the data for the heralded case, which means that the local oscillator is really a single photon. And then I compared it to the unheralded case. Now, when you have down conversion, you probably remember that if you throw away the either beam, which is the herald channel, and you keep only the other signal beam, it's exactly a thermal state.
Mm-hmm.
So we actually are simulating, we're doing an experiment with a thermal-like state onto the beam splitter. And as you could see, the results seem to indicate that we get less information per coincidence event in that case. And I think it's because of the shot noise.
Let's say it again. So which way does it go? So less information with heralding or not?
Oh no, heralding helps.
Heralding helps.
Heralding improves that because that gets you to the Gottesman regime where your local oscillator is a single photon. And if you don't herald at your local oscillator, then your local oscillator may contain 2 or 3 photons. So then you're getting coincidence events which have nothing to do with the star.
Got it. What if you had a photon number resolution in those 4 detectors? Does that help?
No, because you still don't know if the star photon was detected or not. The only way to know that you got a star photon was if you have exactly 1 local oscillator photon and you see 2 clicks.
I see.
Well, there could still be 2 photons from the star, of course.
Yes, because
that's a noise term. We know how to estimate that as well. It just reduces the visibility. So you're right that the Gottesman paper assumes the star emits exactly 1 photon and propagation acts like a beam splitter. Now that's also not a good model. The star doesn't emit a single photon state, but you can redo the whole calculation with the thermal state from the star and get the same results.
Yeah, get the same result. Got it. I see. Very interesting. Thanks.
Thanks for the talk. Would it be a good idea to use some of the principles discussed here to go for quantum microscopy instead of telescopy?
I don't know the answer to that question. I would imagine that the considerations are very different. In other words, in microscopy, you can already do, as large of a solid angle, large of numerical aperture as you want. And you don't need to use just, 2 apertures. You can use the full field in a very well corrected microscope. So I'm not sure there's really any real advantage. I could be wrong.
Okay, right. Okay, thank you.
Any other questions in the audience? I have a quick practical question, Mike. So you're looking into the future and thinking about different challenges like multiplexing and long baseline. What would you envision and the possibility of operating in space, say? How would you envision the architecture of these devices, choosing between, say, free space and fiber and silicon photonics?
Well, if you're asking about space applications like satellites or ISS, then of course, if you try to transmit a single photon between two satellites, you don't have exponential loss, but you still have 1/r² loss. It's the same thing as satellites traveling over the Earth and trying to distribute entangled photons down to the Earth. So there is still a loss there. So in a far science fiction future, if the satellites had quantum memories, which are large buffers, and they could slowly accumulate and fill their buffers with entangled photon pairs, and if you could know the phase reference between these different satellites, and if you could do the Lucan protocol, then in principle, you could have two satellites on opposite sides of the Earth, or even around the moon, or even in solar orbit, and you could do VLBI with very long baselines.
Is there any advantage to moving to the chip in terms of trading off certain things for the ability to do massive multiplexing
On chip?
on chip? I would think that architecturally on a chip, at least, making a complex optical circuit is easier.
Oh yes, when I say diffraction grading, I really mean an integrated circuit with wavelength demultiplexers and then integrated nanowire detectors built into the whole circuit. That's right.
Okay. Any more questions? Anything in the audience on the Zoom?
Yeah, I think I do have one last question. So Mike, this is I think it's a very interesting scheme. So if you think about it, you have photons coming in from the stars, and from there you can already calculate the quantum Fisher information and the Cramer bound, so which would already set a upper bound on the position that it would be able to achieve. So then everything we build locally would just be considered as a receiver or a measurement apparatus. So then we can directly compare the performance of the current measurement apparatus to that ultimate bound. So do you have an idea of how close they are?
I think that is in the Sang paper, and actually Saikot might know the answer to that better than I do. If you remember.
Yeah, so Zeshan, the interferometric measurement, assuming that there is no loss in the fiber and bringing the light to that interferometer, achieves the QFI for that phase estimation problem. On the other hand, Akil is in the audience. I mean, he has some unpublished results where he has shown that if you have more complex problems, like Zeshan, you mentioned these say two stars, so you're trying to estimate the angular separation between them. Then this particular method of UV plane scanning that does not achieve the QFI. You need some more advanced receivers to achieve the QFI.
I see. So there might be some other forms of entanglement that you may be able to leverage.
Exactly.
Closer to QFI. Okay.
Exactly. I mean, right now it appears that, and Akil could correct me if I'm wrong, that the same type of scheme with pairwise entangled bell pairs and along with an interferometric measurement translated to the quantum circuit domain like Michel Lukin did in his PRL, but with a multi-spatial mode sorter at the two telescopes seems to suffice for the simple problem like 2-point sources or estimating the diameter of a star and things like that. But in general, if you say have 3 telescopes or more telescopes, or if there's more complex quantitative image data extraction problems, then it's totally unclear what kind of entanglement or what kind of local processing would be best.
I see. Yeah, that's very interesting.
Just one comment. I know that in the classical homodine, experiments at telescopes. They're developing a optical frequency comb system as a phase coherent, multi-frequency channel local oscillator. And so that would suggest that maybe if we could do multiple mode quantum entanglement, we might also win.
I was just about to suggest that. I know that that Lindran, who is here, he's been working on these frequency comb squeeze light sources. I know that Brian is also interested in that same topic. That could be an enabling technology to do, instead of doing that frequency multiplexing with the heralding signal on the idler like you showed, you could have a comb-like source that will just give you more efficient.
And then you could have multiple mode entanglement.
Exactly.
As well.
Mhm.
So would multi-mode entanglement help, or it has to be a multi-photon entanglement?
Not sure.
Well, what I was suggesting is pairwise entanglement across different frequencies, like say what Olivier Pfister does with his free space bulk OPOs. And you'll need obviously bank of detectors with spectral resolution across that, the free spectral range of that source, and then you will have click events and different detectors, and based on that you'll just take the photons at those frequencies and use it. It will just be like kind of like a multiplier.
Yeah, you don't need a stabilized comb source for that. You don't care about the phases between all the modes in that case. But if you want to have multi-mode entanglement, then you really need to have the phase stability across the entire cone.
That's right. Yep.
Okay.
Any other questions? We've gotten to quantum astrocombs. It's pretty amazing. Well, with that, I guess it looks pretty cold outside where Mike is. We should let him go back in. Can we thank our speaker again?
Del, do you? I know that at this time you would normally present Mike with that certificate. I know that we cannot do that physically, but maybe you could hold it up or something, or I don't know. You can send it to
Unfortunately,
Mike.
it's not in front of me right now, but
I
we
see.
will definitely send that to you, Mike, and we owe you dinner and lunch as well when you're here next time. So thanks a lot.
We'll reserve you a pin. Right.
Yeah.
And a
Oh,
pin.
great.
With
Okay.
a pin on that certificate.
Pin. Yeah, you get a pin and a certificate.
Thanks, everybody.
Thank
Thanks
you,
a
Mike.
lot.
Great talk. Thanks.
Good night.
Thanks, everybody.
Bye.
I feel like I should wave. There you go.